All right, we are live. So last class we started talking about reference frames and we defined a few reference frames. Earth-centered inertial frame, Earth-centered Earth-fixed frame. Then we defined the what we call NED frame, and then we came back and defined body frame, and then the flow frame. So those were the 5 different frames which we talked about. Then we looked at a few reference points, coordinate origin of the body fixed frame. We defined that as CO, center of gravity, center of buoyancy, and then center of flotation. And then we kind of started talking about the generalized coordinates. We looked at the idea that the generalized coordinates and generalized velocities are expressed in the n frame. And then we also looked at the velocity in the B frame is expressed as V vector, where we have UVW and PQR representing the components in the body fixed frame of the translational and the angular velocity. Then we introduced the idea that we will represent a vector in 2 forms, one in the usual vector notation, and the other would be like a vector of 3 coordinates. And that would be a part of a vector of 3 real numbers. And we saw that the equivalence between them is kind of interchangeable, and we said that as we go along the course, we will see a healthy mix of both these notations as and when the situation describes it. Then we started defining a few things, position vector of the body fixed origin relative to the origin of the center of the earth expressed in E frame, and then we started looking at these notations and trying to understand that as we change these notations, what different vectors do they describe. And that is where we were. We had also discussed a little bit about the quaternion, and we kind of talked about the idea that we may not be able to spend more time with quaternions depending on whether we have a sufficient time or not. So we'll see. I'm more inclined now to cover the quaternions as well. So maybe next week we will take up a little bit more on quaternions, because that is the more in thing. As you are looking at robotics and other disciplines, they mostly tend to use quaternions instead of Euler angles. For our ship case, generally Euler angles are sufficient because we don't expect a ship to experience usually the singularity points, and we have not talked about that singularity points as yet, so we'll talk about that today, and from there on we'll discuss why it's not so important for ships, but it is important for other activities like in aerospace or in space, satellites and other things. It's very important to not use the Euler angles because it's possible to become singular. The representation can be singular. That's where we were, and we are going to proceed further from now. Any questions so far? No questions?
No, sir.
All right. So in that case, let's proceed further. So today we'll continue our discussion and we'll discuss a little bit of a kinematics between the body frame and the NED frame. So before we do that, we'll define these quantities which we have seen before. So this is just a summary of those things. So the position vector of point coordinate origin of the body fixed frame OB with respect to the Earth center expressed in the Earth frame is denoted as XE, YE, ZE. And this is the position of the body in the ECEF frame. Okay, we will call that as ECEF position. That's what we'll call it. Now, the same vector, when we express it with respect to NED, which means now we are looking at the position vector between ON to OB. That vector, when expressed in the N frame, is given by Xn, Yn, and Zn, and this is called as the NED position. The position of the body in the NED frame. The body fixed velocity, linear velocity, is given as u, v, and w, and again the notation here is v NB, because we are looking at the body velocity of OB with respect to ON. And that is expressed in the body fixed frame. So this vector is actually expressed in the body fixed frame. So that's why we have the body fixed linear velocity. Then we have the force, FBB. So here we are looking at what is the force that is applied at OB, and that's what this bottom subscript means. And that force vector is expressed in the body fixed frame. So FBB, and it's denoted by capital X, Y, and Z. So the forces in the three orthogonal directions. This is called as the body fixed force. Similarly, we define the moment MBB, and this is the body fixed moment. So which means that this is the moment about an axis that is passing through OB. That's what the bottom subscript means. And that moment vector is expressed in the body fixed frame. That is what is denoted by the stop B. And here we are looking at the roll moment, pitch moment, and the yaw moment. So K, M, and N respectively represent roll moment, pitch moment, and the yaw moment. And this is called as the body fixed moment. Now we have the angular velocity of the body defined as PQR. Again, we saw that this is body fixed angular velocity, and that is why we are looking at in body frame. Okay, and we are looking at what is the angular velocity of the body frame with respect to the N frame. So that's why the N to B. All right, then we have the attitude vector, which is nothing but the set of three Euler angles. And these Euler angles are denoted as phi, theta, and psi. Phi representing the roll, theta representing the pitch, and the yaw represented by psi. In addition to this, we also define two other sets of angles, which are denoting the transformation from the E frame, which means the ECEF frame, with the coordinate system fixed at the Earth's center, to the NED frame. And that is defined in terms of a latitude and longitude. So notice here, L here is the longitude, and mu here is the latitude. We'll have a more in-depth discussion about the longitude and latitude and how to convert that into the flat space Earth in a little bit of a time. So sometime next week, we'll be taking a look at that. Okay, so here what we are doing, okay, all right. So now we'll start to combine. So if you look back at our generalized coordinate system eta, remember that that one was specified as xn, yn, zn, and then you had the three Euler angles theta and psi. A transpose of that, which means it was a column vector. If you look at the first three, that is nothing but P and B expressed in N, so that is that vector. And the last three is nothing but the Euler angle vector theta and B, which we just saw them defined here, right? So I can write this generalized coordinate vector eta as now a combination or the juxtaposition of the position vector of the body in the N frame and the three Euler angles from describing the rotation orientation from N to B. Just a notation, it's still having the same meaning, just that we are making an observation that the 6 cross 1 vector is actually composed of 2 3 cross 1 vectors, which we have defined in our definitions. Is that making sense for everybody?
Yes, sir.
Okay. Then we go on to do the same with the body fixed velocities as well. So here, this also is a 6 cross 1 vector, as we saw before, and that was nothing but previously we saw U, V, W, P, Q, and R. Again, as we saw, the first three are the translational velocities, which again in our new definitions can be represented by this vector V and B. superscript b. So body fixed velocities expressed in the body frame. And the last three, p, q, and r, represent the angular velocity of the body with respect to the n frame expressed in b frame. So that is what we have as the omega nb superscript b. Similarly, since we defined the force vectors and the moment vectors, the generalized force vector, which we defined as tau, can now be expressed as FBB juxtaposed with MBB. Notice that here eta is a vector belonging to a space of 3 real numbers and 3 angles. So this T here represents that it's actually lying between minus pi to pi. Okay, open interval on the right side. So this is what is T. Okay, so since we have 3 angles which are in this modulo minus pi to pi, we are expressing this as 3 real numbers cross 3 of these on the sphere. The angular velocity is a 6 cross 1 vector, all real numbers. Similarly, the force is also a 6 cross 1 vector, all real numbers. So again, as I said, these values lie on a circle basically. So the angles lie between minus pi to pi. Okay, so that completes our definitions of all the quantities that we are of interest to us. We'll now go ahead and start talking about the transformation between the body and the NED frame. We'll now define a rotation matrix between the two frames. So if we have a frame A and a frame B, any general frame A and B, then the rotation matrix will be given as RAB. So notice that this rotation matrix has 2 frames next to it. It is telling us the transformation between those 2 frames. And I'll tell you more about the notation as to which goes on the top and which goes on the bottom and how do we multiply it to get the vector in which frame. So we're going to talk about that in just a bit. Before we do that, I want to talk about some of the properties of this rotation matrix. So this rotation matrix belongs to a class what is called as special orthogonal group of order 3. Okay, so which means that it is basically looking at matrices of order 3. So square matrices of 3 cross 3, which are all orthogonal, and then they have also some special properties in addition to the orthogonality. So let's look at what that is. So this is a set of all rotation matrices R, or all matrices R, such that R is composed of a 3 cross 3 real matrix, and R is orthogonal in nature, and the determinant of R is 1. So when I mean what is orthogonal, orthogonal means that when I take R and I multiply by its transpose, I get the identity matrix. Similarly, if I took the other way around, took R transpose times R, that too will give me the identity matrix. So this in essence basically tells you the inverse of R is nothing but R transpose. So all matrices where this is satisfied, those are called orthogonal matrices. Is that clear for everyone?
Yes, sir.
All right. So what happens is this special orthogonal group of order 3, SO3, is a subset of all the matrices which form of the group orthogonal matrices of order 3. The only additional difference here is that in the special orthogonal group, not only is the matrix orthogonal, in addition, its determinant is 1. Okay, that is what that special stands for in this particular case. Okay, not only are the matrices orthogonal, which means when I multiply them there, we get the identity matrix out, but these matrices themselves, their determinants is 1, which means that if I multiply any vector by this rotation matrix, its magnitude does not change. Its magnitude remains the same. That's what this determinant being 1 means. That if we are not actually scaling up the vector or scaling it down, but the vector remains the same size. Is that making sense?
Yes, sir.
Yes, sir.
Yes, sir.
Ah, fantastic. Okay, now let's look at what is that so-called naming convention for that rotation matrix that we will follow in our course. So in our course, we are going to take a look at a matrices which are labeled as RAB. So the superscript represents to the frame in which we are going to do the transformation, and the subscript represents the frame from which the transformation is being performed. So when I have a matrix RAB, when this is multiplied by a vector VB, which is a vector expressed in the B frame, I get a vector expressed in the A frame as the output. Okay, so in essence, if I wanted to write this R, I'll say the to frame goes here and the from frame goes here, and that vector has to be multiplied to the right side of the rotation matrix. So the vector from the frame will give me a vector in the to frame. Is this making sense?
Yes, sir.
Everybody?
Yes, sir.
Okay. If you have any questions, feel free to stop me at any point and ask me to explain again if something is not clear. Okay, please don't hesitate. As I often keep saying, he who asks is a fool for 5 minutes, he who does not is a fool forever. So please, we want to see more and more questions come into from the audience. Whenever you're not understanding something, please stop me and ask away. Okay. In addition, we'll also introduce some more notation. We will define a skew symmetric matrix. A skew symmetric matrix, and I think this must have been covered in your linear algebra course, but this is just a refresher. A skew symmetric matrix is a matrix which is equal to negative of its transpose. So if I take a matrix S, take its transpose and take a negative of it, I get back the same matrix which I began with. And these matrices, you will find that they have a very special use for many of the cross products and some of the matrix multiplications and what you call vector products that we take. They can be expressed in terms of skew symmetric matrices, and they will be proving to be very useful there. So just to see an example, we'll see if we have a vector lambda cross A, I can represent that as a matrix, skew symmetric matrix that depends on the vector lambda times the vector A will give me the cross product. Okay, so it is an interchangeable computation of the cross product. So let's see this in action so that we can understand this a little better. Give me a second here. A new page. Okay. So let's say that we have the lambda vector given by lambda 1 times I plus lambda 2 times j plus lambda 3 times k. And we have the A vector equivalently as A1 times I plus A2 times j plus A3 times k. So if I want to compute the cross product between these two vectors, how do I compute the cross product? How to compute the cross product?
It is lambda 2 a3 minus a2 lambda 3 of I minus lambda 1 a2 no lambda 1 a3 minus a1 lambda 3 j plus lambda 1 a2 minus a1 lambda 2 k.
Yes, but how to remember this formula?
I usually draw a table with the ijk lambda 1 lambda 2 lambda 3 and
Make
yeah
a matrix.
yeah that's it.
A matrix.
Yes, sir.
So we are basically constructing a matrix whose columns rows are what?
Whose rows are the value of lambda and a, and the columns are the value of I, means that I, j, k, and
Uh,
values.
Tell me again. So the first row will be what?
So first row will be the unit vectors only,
I.
I, j, and k,
Okay. Okay.
and the second row will be of lambda values, lambda 1, lambda 2, lambda 3.
So basically the first vector of the cross product.
Yes, sir.
Then
Second will be AI, A2, and A3.
A2 and A3. And
Yes, sir.
from this, how do we get the cross product?
So just solve this and we will get the
The
cross product
determinant.
We
determinant.
take the determinant of this,
Yes,
correct?
sir.
We take the determinant of this, and that is nothing but lambda cross A. We get out of it. So then once you take the determinant, you will basically see lambda 2 A3 minus lambda 3 A2 times I. So that means I'm taking the cross product between these two plus minus, because the second one is j, and then I have lambda 1 a3 minus lambda 3 a1 times j plus lambda 1 times a2 minus lambda 2 times a1 times k. That's what we get. Right? If we can absorb this minus sign in here, we should get lambda 2 a3 minus lambda 3 a2 times I plus lambda 3 a1 minus lambda 1 a3 times j plus lambda 1 a2 minus lambda 2 a1 times k. Okay, now let's define a skew symmetric matrix. So we saw that a skew symmetric matrix is a matrix which is nothing but minus S transpose, right? So when you look at a typical skew symmetric matrix constructed from a lambda value, you will see it as 0 on the diagonals, and then we have minus S3 if I'm not wrong, yeah. Minus lambda 3, lambda 2, minus lambda 1, and then the opposite is just the sign is flipped because it's a skew symmetric matrix. So we have lambda 3 minus lambda 2, lambda 1. Okay, now the question is, if I take this skew symmetric matrix and I multiply that, so if I want to calculate S of lambda times the vector A, okay, so that is nothing but 0 minus lambda 3, lambda 2, lambda 3, 0 minus lambda 1, minus lambda 2, lambda 1, 0, and I'm taking a product of that with the A vector, A1, A2, and A3. And what do we get? First row will become lambda 2, A3 minus lambda 3, A2. Second row will become lambda 3, A1 minus lambda 1, A3. The next one will become lambda 1, A2 minus lambda 2, A1. And if you see, we got the same thing here. Yes?
So, yeah.
Yes, sir. Yes,
So
sir.
it means that any cross product between two vectors can be expressed as a skew symmetric matrix times the following vector. So which means that the equivalence is there now. Lambda cross A is equivalent to, I form a skew symmetric matrix with the first vector and I take a matrix multiplication of that with A. Everybody with me on this?
Yes, sir.
Yes, sir.
This will prove to be very helpful, especially when we are going to derive our governing equations of motions. Because when we want to derive the Newton's law, we'll see that there will be significant amount of cross products which come into the picture when we take a transformation between multiple frames. And to get those cross products to be expressed in terms of a matrix multiplication, this methodology will come in very handy. So please keep that in mind, and we'll come back to this as we derive the equations of motion. Okay, so that is an interchangeable computation of the cross product, which we just saw in the slide below. Okay, so now we are now in a position where we can start off with doing a transformation between one frame to the other. And we are primarily interested in doing the transformation for the what we call translational velocities. Just see right here. So let's assume that the body has some velocity vector u, and that velocity vector, we want its expression in NED frame, and we also want its expression in the B frame. Okay, so we want it to be expressed in N frame and the B frame, and we want to see how the two can be converted into the other frame. This will really prove to be required as we go forward and formulate our equations of motion. So now we know that the origin of the N frame need not actually be at the origin of the B frame, right? Because NED is at the tangent plane to the Earth, whereas the body need not be on the tangent plane, it may be actually away from it, right? So the body frame's origin need not actually coincide with the O frame's origin. But when we are looking at the velocity vector, the position is not what was of importance. We are looking at the velocity vector. So it's more of a question of the direction that we want to achieve. So in order to make this transformation, we will move from N coordinate frame to a coordinate frame which we will call x3, y3, z3 frame. From there, we'll move to another coordinate frame, x2, y2, z2 frame. From there, we'll move to another coordinate frame, x1, y1, z1 frame. And from there, we'll move to the B frame. You might wonder why I need to do this. This is nothing but we are looking at a rotation angle by yaw, then followed by pitch, and then followed by rho. So our order of rotation will be rotation about the z-axis first, followed by a rotation about the y-axis, and then followed by a rotation about the x-axis. So this is the order of rotation we will follow.
Sir,
Yes.
what about the last one, sir? From x1, y1, z1 to b.
Oh, right. Wait a minute. Where did I mess up? Oh, sorry. I messed up here.
X3, Y3, Z3 same as N frame.
Correct. So the psi is from here to here, theta is from here to here, and phi is from x1, y1, z1 to b. From N to x3, y3, z3, we'll see that this is simply a translation. Because the origin of ON and OB are not at the same location, we'll define a new frame x3, y3, z3, which is parallel to N, which means its x-axis is parallel to N's x-axis, y-axis here is parallel to the N's y-axis, z-axis here is parallel to N frames z-axis. So we are essentially, what we are doing is we translate the NED frame parallel to itself until its origin coincides with the origin of the body fixed frame. The reason why we are doing this is because we are interested really in this velocity vector. It's not the position that we are interested in. So we are only primarily interested in the direction of that vector. Magnitude and direction. Is that making sense?
Yes, sir.
Yes, sir.
Okay. So we translate the NED frame to an X3, Y3, Z3 frame such that its origin now coincides with the body fixed frames B. So now the origin is at the body fixed frames origin, which is at OB. Now from there we start applying our rotations. We first will apply a rotation about Z, followed by a rotation about Y, followed by a rotation about X in order to reach the body frame. Okay, so let me come down here and see. So we first rotate the X3, Y3, Z3 frame by an angle psi, which is the yaw angle, about the Z3 axis. Okay, so if we are looking at the XYZ coordinate system, I'm rotating about the Z3 axis in order to do the first rotation about by an angle psi. So let's look at what that rotation looks like. So let's see, suppose my X3 axis is given here and my Y3 axis is given here. Where is my Z3 axis pointed towards?
Inwards, right?
It will be pointed inwards, right? Because X is going up, Y is to the right side. So Z, the thumb should point into the plane. Am I making sense here?
Yes, sir.
Yes, sir.
Yes, sir.
So the Z-axis is actually pointing downward, and a positive orientation of the rotation is by a right-hand thumb rule. You point the thumb in the inward direction. The rotation is actually happening in the so-called clockwise direction in this particular case. Okay, when I'm looking at it in this particular orientation. So I'm rotating this frame to get to an X2 and Y2 frame, which is shown here, which is rotated by this angle psi, the same angle psi. Is that clear so far?
Yes, sir. Yes.
Everybody?
Yes, sir.
Yes, sir.
Okay, all right. Now let's imagine our velocity vector to be here, which is pointed in some direction. That velocity vector had components u3 and v3, u3 and v3. In the X3, Y3, Z3 frame. We want to find out what is its new value in the X2, Y2 frame. So we take the vectors projections in the X2, Y2 frame and we end up with values U2 and V2. Is this making sense how these values are coming up? We are basically taking the same vectors projection into two different orthogonal directions. Yes, no?
Yes, sir.
Okay, now our task is to relate these three values, the U3, V3 and W3 to U2, V2 and W2. Because the rotation has happened about the z-axis, nothing changed. The component along the z-axis does not change. That is why we'll see that W3 must be equal to W2. Is that making sense?
Yes,
Yes,
sir.
sir.
Okay. So only change will be in U3 and V3 with respect to U2 and V2. And we know that it is rotated by an angle psi, so it can be expressed as U3 equal to cosine of psi minus sine of psi 0 multiplied by this vector U2, V2, W2. Which means if I expand this out, what am I getting? U3 is equal to U2 times cosine of psi minus V2 into sine of psi. Similarly, V3 is given as U2 into sine of psi plus V2 into cosine of psi. And it's easy to see that this relationship holds. So for example, let's take the first one. U3 if I want to get this value u3, what I'll do, I'll take the u2 value, project it onto the x3 axis, which will be u2 times cosine of psi. Is that making sense? The first term here.
Yes, sir.
What I'm doing is instead of taking the v vector, u vector and then projecting it, I'm taking its components and doing the projection. So I take this component, project it onto the x3 vector. I take the other component and also project it onto the x3 vector and then add them up. But you'll see that this fellow will be negative.
Yes, sir.
Right? So that's why the negative sign, u2 times cosine of psi minus v2 times sine of psi. Just want to understand everybody is clear on this?
Yes, sir.
It is clear.
Okay, all right. Now, let's take a look at V3, which is the direction here, this component here. That is nothing but I again take U2 and take its projection on Y3. I take V2 and also take its projection on Y3 and add them up. So I have U2 times sine of psi plus V2 times cosine of psi. And that will give me the total component in the Y3 direction. Yes, no?
Yes, sir.
Yes, sir.
Okay, so that is how we are getting this. And this can be expressed in the matrix form here as U3 is cosine of psi minus sine of psi 0. So that we have this matrix which is multiplied by U2, V2 and W2 to get us U3, V3 and W3. Notice that when I do this multiplication, we'll automatically get W3 is equal to W2. Okay?
Yes, sir. It is clear. Yeah.
Okay. This matrix which we have here is called the rotation matrix with respect to the z-axis by an angle psi. So we'll represent this notation RZ psi. So we have, so far what have we done? We have translated our NED frame to the same origin as the body fixed frame and then made one rotation about the z-axis by an angle psi. And we have reached that so-called intermediate frame x2, y2, z2 frame. Now, from this x2, y2, z2 frame, we will take a further rotation by an angle theta about the y2 axis. Okay, notice that here the rotation is happening so I first make a rotation about the z3 axis, then I take a rotation about the eventual y-axis, which is y2 axis, and then I'll take an eventual rotation about the new x1 axis. That is how we are taking the rotations. So the first rotation we took it about by an angle psi. Now we take by an angle theta. Okay?
Yeah.
All right. Here what we are doing again, we start off with our x2, y2, z2 frame. So here let's say that x2 looks like this and z2 is pointed vertically down. So in that case, where is my z? Where is my y2 axis?
It is inward again, sir.
It is again pointing into the plane, right? So again, if I point my thumb into the plane and I try to understand which is the positive orientation of the angle theta, that angle is again coming clockwise here. Okay, so this angle theta now represents the new rotated angle frame. So that is where we are going to play our x1 axis at an angle theta from the x2 axis. Similarly, z1 axis will also be a rotation about the angle theta from the z2 axis. Notice here that y2 and y1 are the same axis. They are both pointing inwards. Okay, since again y2 axis is the same, this means that when we are taking components of the vector along the two frames which we have defined here, V2 must be equal to V1.
Yeah, yes, sir.
Everyone is clear on this?
Yes, sir. Yes.
Yes.
Anand?
Yes, sir.
Okay. All right. So now what's happening is we now have to express our U2 and the W2 in terms of U1 and W1. And it is easy to see the same process applies again. We will see that U2 is U1 times cosine of theta plus V1 times sine of theta. And you can see that here, U2, where is my pointer? Ah, okay. So we are trying to get this fellow. What we are doing is we are taking U1, projecting it onto the x2 axis, and we are taking W3, W, this is a mistake, this is not W3, this should be W1.
There should be W. Yeah.
This is a mistake, okay, this should be W1. Yeah, we take W1 and then also project that into our x2 axis, and then we add the two up. That will give us the value of U2. When we look at the value of W2, this fellow, we will take the projection of U1 and we'll also take the projection of W1, and you'll see that they'll be in opposite directions. So it has to have a minus sign associated with U1 component. So that is why you see here is minus sine of theta and here it is cosine of theta. The process is pretty much the same as we saw before, and I encourage you to try this out on your own to convince yourself that this is the rotation matrix you get. But I'm hoping that the idea of getting to it is clear in your head. Yes?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fantastic. So this rotation matrix, we will term it as Ry theta. A good way to think about where that minus sign usually goes is it goes before the column which has 1 in it. So if you go back up, you can see that the column which has 1 in it, that is the third column. In the previous column, the sine theta will have the negative sign. That's a good way to remember, but usually it is sometimes one may fall in a pitfall. So having the first principles approach of how the coordinate systems look with a figure, if you can think about it in that direction, that's a sure shot way of never missing out. That minus sign doesn't go in the wrong place. That's usually the best choice. But if you really think that anecdotes help you think about it, then you can think that wherever is the 1, the column before that is where that minus sign will be located. Okay, now we have gotten from x2, y2, z2 frame to x1, y1, z1 frame, and we are only left with the last rotation, which means we want to now move from x1, y1, z1 frame to the body fixed frame, which is xb, yb, zb. So we are going to rotate that frame by an angle phi about the x1 axis. Okay. So again, we go through the same process. So let's say that my y2 axis is here, and I think I have made a mistake here. This should be y1. Y1, z1, w1, v1. Okay. I'm going to correct these and upload them again, just so that we are not getting confused later on. But anyway, let's see. The u vector again is here. We are taking its projections along the body fixed frame are defined as UVW. The projections along the x1, y1, z1 frame are defined as u1, v1, w1. And again, since the rotation is about the x-axis, u1 will be equal to u. So that is why you'll see that in the eventual multiplication, u1 will come out to be equal to u. v1 and w1 will be rotated with respect to v and w in the same manner again. We'll find that if we want to look at, let's say, v1, we'll only take that one example and go ahead with it. So we want to find this fellow. We'll take the value of V, project it on to here, and we'll take the value of W and we'll project it on to here. So since this angle is phi, we will be looking at V times cosine of phi. And since this angle is 90 minus phi, we'll be looking at W times sine of phi as the projection. But W times sine of phi is in the negative direction, so that's why the minus sign comes here. So you see cosine of phi times V minus sine of phi times W. That will give us V1. Similarly, you can argue it out for W1 as well. You'll see the same effect. So eventually, we come up with a rotation matrix for this case, which we denote as Rx phi, okay, which denotes the phi rotation matrix. Here too, you will see the same anecdote still works. The column that I have 1, you cyclically go back one column, you should see the third column will have the negative sign. All right, now we will put all of this together. So notice that in the 3 notations, we started with U3, V3, W3 is given by something multiplied by U2, V2, W2. Then we said U2, V2, W2 is given by something multiplied by U1, V1, W1. And then finally U1, V1, W1 is something multiplied by UV, W. So we can put all of that together and we can express U3, V3, W3 as cascading multiplications of the 3 rotation matrices which we had multiplied by UVW. Notice that UVW is nothing but the velocity in the body fixed frame with respect to expressed in the body fixed frame. And we are taking the velocity of the origin of B with respect to the origin of N. So this is our notation for that velocity. And we see that what we end up getting is actually the velocity of the same object in the N frame is related to the velocity of the object in the B frame through these 3 rotation matrices cascade. So this 3 rotation matrices cascade is essentially a rotation matrix which is telling me how to go from B frame to N frame. That is why the rotation RBN. Is that making sense?
Yes, sir. Yeah.
Yes, sir.
All right. So that RBN, which is the rotation matrix to go from the B frame to the N frame, is nothing but a multiplication of these 3 rotation matrices. And notice that this rotation order cannot be varied. So I can't take some other order of rotation. That will not be the rotation matrix. The order has to be exactly this because we chose the order of rotation as Z first, Y next, and X last. Now, by the property of a rotation matrix, we know that this fellow must be orthogonal. Okay, so if we look at the transformation from N frame to B frame, so here it was B frame to N frame. So if I B frame to N frame, and if I reverse the 2, that should be nothing but the transpose, right? Because of the orthogonality principle.
Yes.
Yeah, and that simply becomes the transpose of these 3 rotation matrices product, which is nothing but the order now changes when I take the transpose of a multiplication. I get Rx phi transpose multiplied by Ry theta transpose multiplied by Rz psi transpose. Is this clear for everybody?
Yes.
If this is not clear, just look at the order of when you take a transpose of multiple product of matrices, what happens? Any linear algebra book you can take, or you can just look for Wikipedia and you'll find that this is the property which happens. Now, coming back to the value from B frame to N frame, I can multiply the 3 matrices out and this is what I get. And you can see that it is by no means a linear matrix. It is having products of cosine and sine of different angles multiplied together and added together. So this is what is our full rotation matrix to go from the B frame to the N frame. Okay, now under the assumption that we have small angles, we'll make the assumption that the cosine of an angle will be approximately equal to 1, whereas the sine of the same angle, if the angle is small, will be the angle itself. Okay, assuming that the angle is small. By making such assumptions, you can see that this will be approximately 1, this will be approximately 1, so the product will be close to 1. This will be roughly be telling you delta psi is what you'll get out. This will give you minus delta theta. This will give you delta phi. This will give you 1. This will give you 1. These three products are really small, so they can be ignored, especially if each of the angles are small, and then these two will give out the value 1. From the top again, you can see that these two are small angles, so their product will be small. So therefore, eventually what is left with is this term, it is minus delta psi. This term can be simplified as delta theta. So these two terms are small. When multiplied, they'll be further small. So what you'll be left with is primarily this fellow. Similarly, in this case, you'll be left with the top term, which is minus delta phi. So putting all of that together, in the small angle case, you can see that the rotation matrix is given by this skew symmetric matrix added to the identity matrix. So if I take the diagonal elements out as an identity matrix, you'll see that what is left there is actually a skew symmetric matrix with respect to the angles. Is that making sense?
Yes.
Yes, sir.
Okay, so this tells you that when the angles are small, since I am neglecting that the compound rotation due to multiple angles, we are neglecting those multiple products of angles here, we will end up seeing that the rotation is actually commutative in nature. I can actually take one angle at a time and find out what is its effect and simply go on calculating what is the total effect. So when the angles are small, the rotation is commutative. Whereas when the angles are large, which is the case when you see here the rotation is not commutative. Okay?
Sir,
Yes.
what do you mean if the rotation is commutative or not?
So which means that I can simply take the rotation due to one angle. So let's say if I have r due to psi alone, what will that look like? 0, 0, 0 minus delta psi, and everything else is 0. Right? Due to phi will look as when the angles are small, 0, 0, 0, delta phi, 0, 0, 0 minus delta phi, 0. So if I have to take the compound rotation, I can take the identity matrix plus the individual fellow here, and I can add the individual fellow here together with it to get the total rotation matrix.
Yes, sir.
Right? I can't do such a thing here. I can't take the individual rotation due to psi first and then just add the rotation due to theta and then add the rotation due to phi. I can't do that here. I'll not get the same thing.
Yes, sir.
right? So that is what I mean that the rotation is no longer commutative. Here it is commutative. I can get away with it. I can just add the components individually up and then be done with it. So I can literally consider each of them as independent rotations and then add the effect up to find my total rotation matrix. But that cannot be done when I'm considering large angles of rotation. Is that making sense?
Yes, sir.
Okay. All right. We will. Okay, well, let me just finish this here and then we'll stop. So the body fixed velocity vector in the body frame in n can be expressed as, so this velocity vector in n can be expressed as the position of OB with respect to ON expressed in n. I take a differentiation of that. So I'm taking nothing but d by dt of position of the B frame with respect to the location with respect to n frame expressed in n frame. That is nothing but the velocity because n is an inertial frame. For all practical purposes, okay? Unless and until you're looking at terrestrial navigation, n is an inertial frame. So therefore, I can take a differentiation of the position to get the velocity. But this velocity is related to the velocity in the body fixed frame through this rotation matrix. And that rotation matrix actually depends on these Euler angles between the two frames. So similarly, if I wanted to invert this relationship, I can get the body fixed velocities as the inverse of this rotation matrix times the derivative of the position vector in the inertial frame. But since the inverse is nothing but the transpose, that converts into the transpose times this. Okay?
Yes, sir.
Yes, sir.
So what we have now essentially done today is we have taken a look at how the linear velocity of the body can be expressed in the N frame and in the B frame and how to interchange between them. So if I knew one, how to find the other, and if I knew the other, how to find this one, we have found an interchangeable formulation for it. So that is where we'll stop today. Next time we will do the same relationship. We will try to find a similar relationship for the angular velocity. So today we have discussed the linear velocities. Not linear, actually, translational velocities. Translational velocity, how it transforms between the N frame to the B frame. That's what we have looked at. Next class, we'll look at what happens with angular velocity. And you'll see that it will not be exactly as same as what we saw with the linear velocity or the translational velocities. And that is the main reason why you have a problem with Euler angles becoming singular at certain points. And we'll discuss that in the coming lecture. Okay, any other questions before I stop recording? Okay, if not, let me stop recording.